By now, if you're an architect working on Azure infrastructure designs, you've probably come across Private Link. Probably if you're an established customer on the platform, you're also using things such as private endpoints, private link services to access Microsoft PaaS resources, maybe your own resources. One of the common questions that crops up when you get into the weeds of Private Link is how the data plane works in respect to the Azure SDN, how that interacts with VNet peering, and the implications on cost. For example, in this diagram here, if this virtual machine here accesses this private endpoint, what does that look like in terms of packet forwarding? Do I pay for VNet peering plus private endpoints? What if that private endpoint's in a completely different Azure region to the actual private link service that it's trying to access? And that's what we're going to unpack in this video. You may have found this video just because you're subscribed to the channel or because you specifically looked for the nuances of private link. Maybe even you've come across these documents here and you've seen breadcrumbs to the fact that you can run private link in a global fashion with no regional restrictions. Maybe you've seen a similar statement here in the implementation documentation talking about the global nature of private link, or maybe you've been into the pricing calculator. With private endpoints, you pay a charge, static charge for the private endpoint itself, but then you pay for data in and out of that private endpoint. And there's a little nuance here to the pricing, which is important to understand, which is while accessing private endpoints from a peered network, you're only charged for the private link cost. And we'll get into that. Basically, you're not double charged for that. So let's jump to our whiteboard and show our test setup here. I've got in purple my components inside of West Europe, a virtual network, a test virtual machine with the IP 10.10.3.4. Also inside of West Europe, it's important to understand it's in the same region, I have a storage account and I've enabled a private endpoint for that storage account. But that private endpoint lives inside of a virtual network inside of East US. I've got an East US VNet here. I've globally VNet peered those virtual networks, so there's SDN reachability there. And my private endpoint's got the IP address 10.1.7.10.5. So a really interesting exam question, which I would put on the AZ700 if I was writing it, would be if this virtual machine here accesses this storage account via private link and it actually uses the private endpoint over here, how would you expect that packet to flow? So pause the video now and maybe answer the question and then come back and we'll explain how it actually works. So you might have guessed that the traffic would go across global VNet peering into the private endpoint, back across the Microsoft backbone, and then into the storage account. What I will show is that is not actually how it works. There's intelligence in the Microsoft SDN, which effectively goes, okay, I've got a source here. It's accessing a private endpoint in a peered VNet, whether it be globally VNet peered or regionally VNet peered. And that VNet peering is important because when you've got two VNets together and they're talking behind the scenes, that VNet peering relationship is very important when it comes to the underlying SDN. It's clever enough to realize that, oh, this private endpoint is actually then pointing me at a resource inside of the same region. So the actual data flow here will go straight to the storage account, but it will use the security, logic, and intent of the fact that the storage account can only be accessed via private endpoints. It can make your head turn around backwards when trying to understand this, but once we do understand it, it's pretty powerful. Okay, so let's demonstrate this behavior. Here I've got my storage account, and we'll see I've got a private endpoint enabled for that. If I click on the private endpoint, we can see that it is inside of this VNet, East US, so this green VNet here. I can click on the NIC, you see 10.1.7.10.5. That's the IP address here. I've globally VNet peered these VNets. I can jump on the client here. You see it's got the IP address 10.10.3.4. So this is my test VM in my VNet in West Europe. So we would expect if you're pinging from a resource on a Azure node inside of Amsterdam, you're pinging all the way across the ocean to a machine on the east coast of the US, you're going to have a latency there due to the speed of light, and even the best cables there run about 60 milliseconds. If I ping 10.174.10.6, notice that I've also got a virtual machine here inside of my hub in East US. I'm pinging from West Europe VM to East US VM. And we can see we get a latency there of about 80 milliseconds. So that's expected. That's going across Microsoft Backbone, across global VNet peering. Now, where this gets interesting is, what if I try and reach my storage account? Well, I'm going to, behind the scenes here, I've done all of my DNS integration so that when I look up my storage account FQDN, I get back the private endpoint IP. So you see here, when I ping my storage account FQDN, I get back 10.1.7.10.5. In the same virtual network, actually in the same subnet, but it's a private endpoint, which we looked at earlier, 10.1.7.10.5, mapped to my storage account. So the latency I've got in the SDN from my VM to that NIC looks like it would be the same, right? However, if I do a TCP ping to my storage account, look at the latency. I'm getting less than 2 milliseconds, which is what you would expect when you're in the same region as that resource. As I said, what's happening here is the SDN is intelligent enough to realize that this NIC, even though it exists in a different Azure region, is fundamentally linked here. You can almost think of it as we bypass the long haul path here because that NIC is in a peered VNet. Once you understand this behavior, if you're working with global topologies, you might get more conscious about where you place your private endpoints. Do you place them in the spoke? Do you place them in the hub? We can take this testing one step further to show you how this would work with an on-premises interaction. So I've expanded out my lab here in West Europe to include an express route gateway, which is connected to an express route circuit, which is actually in London, to my on-premises data center that's actually in Paris. So my traffic here from a test virtual machine in Amsterdam will go to London and then to Paris. It'll cross the English Channel twice. I would expect in the region of 20 milliseconds for that traffic when it's going to a resource in West Europe. Okay, on the right-hand side now, I've changed the client. So this time I'm on my on-premises client where I'm testing from. We can just verify reachability, first of all, from Paris on-prem to my VM in West Europe. So we can see we're getting 15 milliseconds, pretty good latency to go, let's say, across the channel and back again. If I ping 10.174.10.6, I'm going to come into Azure in West Europe and then across global VNet peering with this other VNet. So on this box here, on the peering session, I've ticked the box for user remote gateway. I've got reachability here. So we can see we're getting a latency there of about 87 milliseconds, which again, that's what we would expect for traffic to come into the Microsoft backbone and then go across the ocean to East US. That was this flow here. But again, we can use the knowledge that we have now of the private link data plane to understand how this would work if we're accessing a private endpoint. Again, I've done my relevant DNS integration on premises so that when I contact my storage account FQDN, I am getting back the right private endpoint IP, which we know lives inside of East US. But look at the difference here. When I perform a PS ping, so I'm contacting the storage account on port 443, despite it looking like the packet's going to the private endpoint in East US, my latency is only 15 milliseconds. So either I'm invalidating the laws of physics in terms of the speed of light, or the Azure SDN is clever enough to know to hand off the packet locally. The traffic's coming into the express route gateway. The express route gateway's got a packet destined to the storage account, And because this express route gateway is in a peered VNet to the private endpoint, and I'm not forcing that traffic through an intermediate device like an NVA or an Azure firewall or a virtual WAN hub, etc., it's clever enough to realize that, oh, there's a better path here. I'll send the traffic straight to my storage account. Okay, let's bring this home now by talking about a scenario where you wouldn't benefit from that optimized data path. To highlight a scenario where you would incur the additional latency. If I move my private endpoint in East US and put it into a spoke VNet, and then I've got an intermediate hub VNet before I contact West Europe, this fairly classic design that customers use where they would forward traffic across global VNet peering to an NVA, which would perform IP forwarding onwards to spoke resources. Normally you'd have an equivalent NVA over here and more spokes hanging off here, a very common pattern. In this scenario here, you wouldn't get the same behavior because this resource, when it reaches out to this private endpoint, these two VNets are not peered directly. They are two VNet peerings away, a global VNet peering to the hub and a regional VNet peering to the spoke. And in this scenario, when this test VM, when the SDN component behind the NIC of 10.10.3.4 says, how do I get to 10.174.10.5? Ultimately, what's getting that traffic there would be a UDR to an intermediate device in this region, which would then forward traffic almost to the private endpoint. And if you were to retest in that scenario, you would see a latency in the region of 80 milliseconds for that inter-time zone transit. All right, I hope you found it useful. If we could distill this video down into one simple point, it would be, remember that private endpoint NICs are different to virtual machine NICs in respect to how packet forwarding works. And if we understand that, we can make it work to our advantage in terms of where we place those private endpoints and the impact it has on our latency to the ultimate PaaS destination. Thanks a lot. Catch you in the next one.